Welcome to today's explainer. So I want you to think about the human body for just a second. We usually picture it as, flesh and bone, right? But honestly, at a microscopic level, it's really the most perfectly tuned, incredibly complex plumbing machine on the entire planet. I mean, we're talking millions of pipes, microscopic filters, high-pressure pumps, all working in absolute total harmony every single second of the day. But what actually happens when that flawless system springs a leak? Well, today we're going on a bit of a journey. We'll start with perfect biological harmony and go all the way to catastrophic system failure. We're going to explore the true mechanics of fluid balance and the totally fascinating and honestly sometimes chaotic pathology of edema.
Okay, let's take a quick look at our roadmap for today. First, we'll cover the perfect balance, homeostasis. Then, number 2, the push and pull. 3, system failure, understanding edema. 4, transudates versus exudates. And finally, 5, the clinical consequences of edema. Let's get right into it.
Starting off with section 1, the perfect balance, homeostasis. It's kind of crazy to realize just how much of you is actually fluid. We are, quite literally, walking bags of water. Total body water makes up a massive 60% of body weight in males, and it's around 50% in females. So when you look in the mirror, you're really only looking at about 40% solid mass, and just a whole lot of liquid. And managing that massive volume of water, well, that is your body's full-time job. And that management job actually has a name. It's called homeostasis. Basically, it's the mechanism by which the constancy of our internal environment is maintained. Early physiologists had this beautiful term for it, the milieu interieur. Your body fiercely, and I mean fiercely, protects this internal environment just to keep that massive 60% of water exactly where it needs to be. It's a dynamic, non-stop balancing act. Now, while a lot of that fluid is locked away safely inside our cells, a really huge portion sits outside them in what we call the extracellular fluid compartment. Let's break that down. 12% is interstitial fluid and lymph, that's the fluid just bathing your tissues. 9% is locked up in mesenchymal tissues, so things like cartilage and bone. And 1% is transcellular, like the fluid lubricating your joints. But I want you to notice that 5% right there, the plasma. That represents roughly 3 liters of fluid acting as the main, high-speed pipes of our physiologic plumbing system. And the fluid running through those pipes, it's regulated with just mind-blowing precision. Take a look at this number. 7.4. This is the exact pH your blood absolutely needs to maintain. Not 7.3, not 7.5. Your blood pH is locked in at exactly 7.4, give or take a tiny 0.05 margin. To keep this incredibly delicate balance, your lungs are constantly breathing out carbon dioxide, your kidneys are filtering out hydrogen ions right into your urine, and these complex chemical buffer systems in your blood are neutralizing acids on the fly. It is a literal masterpiece of engineering.
All right, moving on to section 2, the push and pull.
Enter Starling's law. You can think of this as the ultimate rulebook for the body's internal plumbing network. Starling's law is the physiological rule governing fluid exchange between that 5% plasma in your blood vessels and the 12% interstitial space surrounding your cells. And honestly, it all boils down to a constant microscopic tug-of-war between two very specific opposing pressures. Okay, first up, hydrostatic pressure. Think of this as the push. It's the literal physical pressure of blood pumping out from the heart, driving fluid out of those microscopic capillaries. It starts out strong at 32 millimeters of mercury on the arterial side, and then drops to about 12 on the venous side. Opposing that push is oncotic pressure, or the pull. This one is driven by large plasma proteins, mostly albumin, that act almost like tiny molecular sponges. They create this constant 25 millimeter pull, drawing fluid right back into the capillaries. Push and pull, out and in, happening every single second of your life. But as with any incredibly complex system, things can and do go wrong. The pipes can get blocked up. The pump can fail. Those molecular sponges can degrade. So the big question is, what actually happens when the plumbing breaks? That brings us to section 3, system failure. Understanding edema. The clinical term for this chaotic aftermath is edema. Simply put, edema is the abnormal and excessive accumulation of free fluid in your interstitial spaces or serous cavities. When that delicate push and pull balance we just talked about gets disrupted, well, the fluid has to go somewhere, right? And it ends up pulling in places where it absolutely shouldn't be. So the crucial thing here is understanding exactly how this happens. Let's run through the main villains of the system, because edema usually stems from one of these 5 main plumbing failures. First, decreased plasma oncotic pressure. Think of this as a weak sponge. If you lose albumin proteins, say from liver or kidney disease, you lose your pull, and the fluid just leaks out. Second is increased capillary hydrostatic pressure. That's a pump working way too hard or getting backed up, like in heart failure, pushing way too much fluid out. Third, lymphatic obstruction. This is when the body's natural drainage pipes literally get blocked. Fourth, increased capillary permeability. This happens when inflammation or toxins physically damage the pipes, making them leaky. And finally, fifth, sodium and water retention. This is where the body's hormonal systems mistakenly hoard salt and water, which basically overloads the entire system. Next up, section 4, transudates versus exudates. When doctors actually pull a sample of this edema fluid, they're looking for very specific clues to figure out exactly what kind of leak they're dealing with. If it's a transudate, the fluid is basically just watery plasma pushed out by pure mechanical pressure, like you'd see in heart or kidney failure. Because of that, it has low protein and a low specific gravity. But if the pipes were damaged by, say, an infection or inflammation, they'll leak much larger molecules, and that creates an exudate. High protein levels and a high specific gravity instantly tell a clinician, hey, we are fighting an inflammatory attack here, not just a mechanical pressure problem. And that leads us to our final part, section 5, clinical consequences of oedema. Let's take a look at the kidneys first. The kidneys are your body's master filters, and they can actually cause swelling in 2 very different ways. First, we have nephrotic renal edema. This happens when the kidneys get damaged and literally start leaking your essential proteins right into your urine. Remember those molecular sponges we talked about earlier? Well, they're gone. And without them, there's no pull, which leads to severe, generalized swelling all over the entire body. Contrast that with nephritic renal edema. In this case, the kidneys mistakenly hoard sodium and water, so this is a volume overload problem, and it usually results in milder swelling, particularly in loose tissues like around the face and the eyes. Then we have cardiac edema, which is, as you'd guess, intimately tied to the heart pump failing. When the heart can't effectively pump blood forward, the pressure backs up in the veins. This massively spikes that hydrostatic push pressure we discussed. What's truly fascinating about cardiac edema is that it's highly dependent on gravity. Like if a patient is standing or walking all day, that excess fluid gets pulled straight down, pooling heavily in their lower legs and ankles. But if a patient is bedridden, gravity pulls that exact same fluid into their sacrum or lower back.
But listen, edema isn't always something you can see from the outside, and this is where the stakes get incredibly high. Pulmonary edema occurs when the system backs up directly into the lungs. So instead of being filled with air, the delicate lung alveoli fill up with this heavy, frothy fluid. The patient is literally drowning from the inside. And equally terrifying is cerebral edema. Swelling in your arm is one thing, the skin can stretch, but swelling of the brain is uniquely dangerous because it's completely encased in a rigid, unforgiving bone shell, your skull. There is absolutely no room for the fluid to expand, and that causes devastating pressure right on the brain tissue itself.
Okay, we've covered a lot of heavy clinical ground today, but I want to leave you with a thought that brings all of this incredibly complex science right back to your everyday life. Have you ever been on a really long flight or maybe stood on your feet for a super long shift and suddenly found that your shoes feel uncomfortably tight? Well, that isn't just fatigue. That is a real-time microscopic battle happening inside your body. You are physically experiencing the force of gravity temporarily overwhelming the delicate balance of Starling's law. Your hydrostatic pressure got just a little too high, your internal sponges fought back, and a tiny bit of free fluid pooled right in your interstitial spaces. It is a pretty wild reminder that we aren't just solid beings. We are literally walking oceans, constantly managing a beautiful, precarious internal tide. Thanks so much for joining me on this explainer, but before you go, it really makes you wonder what other microscopic battles is your body secretly fighting and winning at this very second.